All right, here we have a problem from chapter 7. Good one to get us in practice after taking a long break. So chapter 7, number 32. Not a hard problem, but it's a good problem conceptually to think about what's happening here. So I'm going to give you a few seconds to read it, and then stop the videotape, go do the problem, and then come back, watch the video, and see how I do it. Make sure you get the same exact values. All right, so here we go. Let's look at the situation here. We have Bob. Throwing a rock. He throws a rock and it has a velocity of 30 meters per second. Okay? When you throw a rock, you're actually accelerating it the whole time your arm is moving, and that's about 1 meter that you're accelerating the ball from rest up to this velocity of 30 meters per second. So the ball feels an initial velocity of 0 meters per second, and this is the final velocity of 30 meters per second in a distance of 1 meter. Well, this doesn't have anything to do with a free body diagram at this point, because all we're doing is accelerating a rock. And so we can just use our constant acceleration equations to figure out what the acceleration is. So if I use this equation, I know what the initial velocity is, I know what the final velocity is, and I know the distance that it traveled. I can solve this for A. So if I rearrange this equation, I get v squared minus v naught squared over 2 times x minus x naught is equal to a. Well, I know all that, so I can plug that in. I can say a is equal to the final velocity of 30, so this is 30 squared minus 0 squared over 2 times 1. Okay? Now when I do that, and I solve this for the acceleration, I get the acceleration is equal to 450 meters per second squared. A significant acceleration, but you have to get it going from 0 to 30 meters per second in just a short distance. Well, that means Bob has to apply a force to create this much acceleration. So the force that Bob applies, or the net force, just has to equal the mass times acceleration from Newton's second law. I have the acceleration, I have the mass of the ball. If you remember, the mass was equal to 500 grams or 0.50 kilograms. We're keeping 2 significant figures here. So the force that Bob has to apply is equal to just 0.5 times 450 or 225 newtons. Right, but Bob feels the same force in the opposite direction. Okay? So Bob feels a force of 225 newtons going the opposite direction. We want to know what his recoil speed is. But to get his recoil speed, we have to know what his acceleration is. So this is the acceleration of the ball. Over here, I'm going to do the acceleration of Bob. If you can still see that. So Bob, we have the S net of Bob is equal to ma. In this case, we know the force now is 225 newtons. It's actually negative 225 because he's going to feel force to the left, equal and opposite, divided by his mass. His mass is 75 kilograms, so significantly higher than the ball's, and he feels a force of negative 3 meters per second, and acceleration negative 3 meters per second squared. Okay? Now to figure out his velocity, which is what we want, the velocity after he throws that, or his recoil speed, we can plug this into here, but we really can't, because his arm moves 1 meter, but he doesn't move 1 meter. So we can't plug that in and try to solve for this. We don't know what his change in distance is during the time he's throwing it. But we can figure out the amount of time that it took for this throw to occur. And during that time, it's going to be the same that he feels a recoil. So I'm going to figure out the time, let me do this in green, from the first part. So if I do this equation, constant velocity equation again, I can solve this for t. Figure out how long it took his arm to throw that ball. If I solve for this, I get v minus v naught divided by a is equal to t. Or t is equal to the final velocity of 30 minus 0 over my acceleration, which was here, 450. And you get that the time, in this case, is 0.067 seconds. So that's how long it takes him to throw the ball. Then I can figure out his velocity because I can just use this equation. Now we have t, we have a, and we have the initial velocity 0. We can figure out what the final velocity is. So it's going to be v is equal to v naught plus at, or his final velocity is equal to, that's 0. A is minus 3 times 0.067. His velocity is equal to negative 0.2 meters per second, 0.20 meters per second. Or he's going about 20 centimeters per second. Fairly slow. Normally you would never feel this because you're not throwing something on frictionless ice. But if you were, that would be the case. You would move backwards with that recoil speed. All right, so this is the answer to question, what is his recoil speed? And this is the answer to the force he applies, part A. So this is part A.